Hello everybody. Today we shall learn a method of solving the Maxwell's equation, probably the most useful method of solving the Maxwell's equations. So let me first write down what we have written last time. We had the Maxwell's equation in terms of the electric fields and the magnetic fields. And I told you that you are not allowed to forget these if you are doing any physics. And we also defined potentials. One was the vector potential A, and other was the scalar potential phi. The electric fields and the magnetic fields we wrote down in terms of the scalar and the vector potentials. And then there are these two equations which are supposed to let us allow to calculate the electric field and the magnetic fields. Remember, mu naught and epsilon naughts are constants, and they're up to your choice of the units of charges, etc. And mu naught time epsilon naught can also be written as 1 by c square, c being the speed of light. So this is one set of equation for the phi, and for A they looks like the following. Of the same quantity, gradient of the same quantity, divergence of A plus 1 by c square del A del T. And to solve these phi and A, we need a choice of gauge. We need to tell what is divergence of A. So if I do that, we are supposed to be able to solve for phi and A, and then if I know the solution for phi and A, I can use B as curl A and E as minus grad phi minus del A del T to get the electric fields and the magnetic fields. Now these equations, if you look at these equations, and even the electric fields and the magnetic fields can also be casted in equations of the same form. They have these general properties. So you are trying to solve for some quantity. So let me write that as phi. So it can be one component of the electric field, one component of the magnetic field, or one component of the vector potential A, or the scalar potential phi itself. I have an operator operating on it. So I write it this way. It's like an hammer. So that's an operator operating on the potential. And in the right hand side, I have a source term. So this is a source. I call it a source term because if you see in the right hand side of these equations, I have these terms. I also have this del t and the gradient term, but we'll see that they can be fixed if I choose the proper gauge. That is, if I choose divergence of A, then something happens to those terms. But in the right hand side, I will always have these source terms. And the operators in this particular case are this grad square. And if you remember, grad square was 1 by c square del 2 del t2 minus the Laplacian. So that's my operator. So this is my operator. So these are partial differential equations, and with these I also need the boundary conditions. So if somebody tells me what are the operators, what are the source terms, and what are the boundary conditions, I should be able to figure out what is phi. So let us list those. The solution for phi depends on the operator, the source, and the boundary conditions. Okay, and we'll see that the mathematical method that we learned today to solve a particular equation in particular, but that operates or that works for all partial differential equation of this kind. There is one more important thing here is that it's a linear equation in phi. So all linear equations of this kind can be solved using the method that we will learn today. Though for a particular case, but it can be used for all linear equations. Now, physically, what are these different terms? What is the meaning of these terms? Well, the operator will tell you which theory you are working on. So in this case, it's the theory of electrodynamics. So that will decide what operators will come here. The source term is related to the electrical sources. Where are those sources? But you see, whenever you work in a practical problem, so in a practical problem, we cannot know source distribution at all place at all and at all time. Right, obviously you cannot know it for all time. If you are doing the measurement, you cannot know what was the source distribution by any measurement that you perform before you took birth here on Earth. And obviously, you will die at some point, so you will not be able to know what are the source distribution after you die. You cannot even measure it very far away part of the universe, at very far away part of the universe. So you always have a limitation over which you can measure. And that is where the boundary condition comes in. Because if you see, if I did not meet the boundary condition, I could have, if I assume that I can solve this equation of phi for phi at all space and all time without requiring any boundary condition, means then it will mean that I have to know about the source distribution at everywhere in the space at all time, in past and future and present. Now that is not possible. So what happens is that it turns out that it is enough to know the source properties inside a finite volume. Now, when I say finite volume, if your source function is a function of x and t, like these rho's and j's are, then obviously that volume is a volume in space as well as in time. A volume in time essentially means that from a particular past time to a particular time in future. So that is what is required to know. That is what is enough to know. But then we must also know certain information, what that we learn today, about the field itself. At the boundary of the volume. Okay, so it turns out that if I know these two things, that is, what are the source distribution inside my volume, and what are certain properties of the field, again, what are those we will know at the boundary of the volume, those will be called the boundary conditions. Then there is a unique solution for phi inside everywhere in the volume. And that's important, inside the volume. I did not say there is a unique solution for phi everywhere. That I don't know. But at least I can prove that inside the volume, the solution of phi is unique. Okay. So now this is the setup that we are trying to work out today. Given these informations, how to get what is phi. Okay. And now to do that, we will solve for a we will solve for an easier problem first, which is the problem for statics. So what do I mean by statics? So I am looking at these equations, the Maxwell's equations, either in the form of electric field and magnetic field, or in the form of the potentials. And we try to solve for the cases where none of these quantities vary with time. So that's the problem of statics. And let me write down the problem of statics, and that you can see. So this is the problem of statics. So none of the quantities has any time dependence. in this particular case. And physically, you cannot have an electromagnetic system which is having a static condition without any external force. But that's a separate discussion. We'll not go into that discussion. I just provoke you to think about it, why we cannot have the problem of statics without any other force other than electromagnetism. But if I consider the problem of statics, those equations that we wrote above, they boils down to the following equations. So you get a Poisson equation for phi. So this we call Poisson equation, as you know very well. And you get three Poisson equations. Well, if I consider the three components of A, it looks like this. Okay. Remember that rho now is function of the position variables, three position variables only, and J is also a function of only three position variables. So x component, y component, and z component of J will be function of those. And because of that, phi is also a function of only the position variables, and that's the functional form that we are trying to get by solving these equations for a given boundary condition. And same for A. If I want to look at the Cartesian components of this equation, then what do I get? I get grad square phi equals rho by epsilon naught. I get grad square x component of A equals, this is minus, mu 0 jx if you look at these, they have exact same form. They have exact same form. Well, why do I say that? Well, if you have to write it down, for example, in spherical polar coordinates, the operators will look different. But if you write down them in the Cartesian coordinates, the operators are all same. So it turns out that it is better to find a solution for these equations, which I need to know only to learn how to solve this equation, particularly grad square phi equals, say, let us take this equation. So if I know how to solve this, then I know how to solve any of these, because what all I have to do is I have to replace 1 by epsilon naught as mu naught, which both are constants, and rho by j, so they are just two different functional forms. Whatever I will get is a corresponding phi. The component of j that you put in over there for rho, you will get the component of phi. And when you are done with solving them in the Cartesian, later I can choose to write the solution down in any other coordinate system, because I know how to transfer coordinates to several coordinate systems, right? So this is the setup, this is the equation that I want to solve. So this is what will be our pet equation for some time now, at least rest of today, and try to see how to write down the solution for phi for a given rho and boundary condition. Okay, so to do that we have to go through a certain mathematical developments, and that's what we will do today, and that's what we'll do now. So let's start. So let me remind you of something that you know very well. It's called divergence theorem. This is a result from vector analysis. What does it tell you? It tells you that the volume integral of the divergence of a vector over an entire area, over an entire volume, sorry, is equals to a surface integral over the surface which is enclosing that volume on the normal component of the same vector at everywhere in the surface. Okay, so I have written down the divergence theorem. Let us now talk about what does it say. Well, I have a volume. So let me first draw a volume. So this is my volume. Okay. Well, what I have just drawn is the surface that is enclosing the volume. Now, obviously, I cannot draw a three-dimensional volume on the two-dimensional sheet of paper. So what I have drawn is a representation of a two-dimensional surface using that curve. Okay. Now, what is the left-hand side telling you? Left-hand side is telling you that there is this A which is known everywhere inside the volume. Okay, so let me move it a little bit here. So A is to be known. To calculate the left hand side, A has to be known everywhere inside the volume. And let us call the volume as V and the surface as S, just to have some notations for them. Once you know the A, actually you don't need to know the A, but you need to know the divergence of A. But let's say that we know A. Estimate divergence of A everywhere in V and add them up. So that adding up part is the integration, right? That you know that integration is the limit of a sum. And if I do this exercise, what will I get? I'll get the left hand side of the integral. Now, the divergence theorem tells you is that you can calculate the same thing in the following way. You don't need to know everywhere inside the A, everywhere inside volume. You need to know A in the surface of the surface is a closed surface. So this is a closed surface, and that is important, and that is what is denoted by the circle around the integral, the right hand side. And this is the surface which is closing the other volume, the volume, that integral that you are doing in the left hand side. Then you take the component of A normal to the surface. And obviously everywhere in the surface. So I take, so if I try to draw a patch of the surface here, the local patch, there will be a local normal to the surface. This is the direction of the local normal, so unit normal if you wish. And I call it with a prime sign here. So you see, whenever I have written a prime, this prime essentially means that this is integrated over. So if I am this at this local point, my A vector at this point can be like going in any direction. All I have to do is that I have to take the projection of A along that local normal. So that is A dot n cap, right? So take the component of A normal to the surface everywhere and sum them up. Now this is very interesting that the summing up is obviously the integral, and that is the center exercise will give you the right hand side of the equality. Now you see, it's very interesting. The left hand side and the right hand sides are equal, and that's amazing because in the left hand side you have to know A everywhere inside the volume. That's a huge amount of information that you need, and then once you do this integral you get some number. The right hand side is telling you the same amount of information you can get just by integrating something on the surface of this surface which surrounds this volume. Is not it very interesting? Because for the left hand side you require a lot of work to do, right hand side you do a less amount of work to get the same information. So it's kind of a mathematical trick. But this is just to remind you of the divergence theorem, which we will use shortly. And what we are now aiming at is the divergence theorem was first showed by Carl Friedrich Gauss, and now we'll look at a different theorem or set of identities which was done by Green. And these identities can be achieved using the divergence theorem. So what do I do for this? So I have the same setup where I have a volume which is enclosed by the surface S. So I have volume V enclosed by the surface S. Okay. So I choose a function two scalar functions. In physics, we sometimes call them fields also because they are the quantities which has values everywhere in x, everywhere in space. So these are functions of x, and that's what we call field in physics. But the field also have a mathematical description. Field is also used for something else in mathematics, but this is just two functions which are functions of x. And these functions are well behaved inside the volume. And we can construct a vector field out of this function. And this has no physical significance at this point, it's just a mathematical construction. We are essentially trying to use one identity to go to another identity in vector analysis. So this vector field, which conveniently we call A, is phi times gradient of psi. Well, gradient of psi gives me a scalar function. Sorry, gradient of psi gives me a vector function, that is three functions. And then I multiply it by another scalar function. So I get three functions again, which I call the vector A. And now this is a vector A, and this divergence theorem is true for any vector which is well behaved, vector function which is well behaved inside that volume. So what I do is I just use phi grad psi in place of A. Okay, so what will I get if I do that? So I get a volume integral. Remember that the left hand side was divergence of A, and A is now phi gradient of psi. D cube x prime is my volume integral. And in the right hand side, I have grad psi dot n cap dA prime. Okay. Now, before I go to the next step, let us work out the integrands separately. So, what is this? So, this I can write as the operator will operate on the first function, scalar function first. So, that will be a gradient operation on phi, and then it will operate on the vector grad psi, and that will give me a Laplacian of psi. In the right hand side, I have this grad psi dot n cap. Grad psi gives me direction of change or directions of change and their rate at different right. So grad psi, if I ask the question what is the unit vector along grad psi, that tells me what is the direction of change of psi, and I can also take its components along the different coordinate unit vectors, so that tells me which direction it changes how much. And when I do dot n cap, this entire thing will give me the projection of that change along the direction of the normal to the surface. So this I can write as how psi. So this means that this will tell me how psi changes along the normal to the surface. So I can write this as del psi del n prime. So this is grad psi is the change along all three coordinate unit vectors. I am taking the projection of that vector along the normal to the surface. So change, or rather rate of change of psi along n cap, right? So I will write this here and this there. What will I get? I'll get the following. Dot product with gradient of phi right. So that is these two replacements in the left hand side. That's a volume integral that is equals to the surface integral of phi, and grad psi dot n cap is del psi del n cap. This is another identity This is called Green's first identity. Okay. Now, see, we chose A as phi grad psi. I could have chosen A as psi grad phi also. And you can imagine what will happen if I do that. I will interchange phi with psi everywhere. So let us write it down. The present choice gives me gradient of psi dot gradient of phi plus phi grad square psi and I write the same thing, the same Green's first identity, interchanging phi with psi. Easiest thing to do in the world. If I subtract one from the other, you see that the first term is exactly the same. A dot B is obviously B dot A. So I can write after subtraction, and I choose to subtract second minus one, the first. That is just for our later conveniences. That is what remains in the left hand side, which is a volume integral again completely. In the right hand side, I get this is the Green's second identity. And we are doing all these, remember, to get to a method to solve the Poisson's equation, right? So now let us have this Green's second identity in the top of our head, and let us come back to Poisson's equation. So what was Poisson's equation? Or what was the equation that we are trying to solve? Well, Poisson equation, again, as I would like to emphasize that we are trying it as an example here, because in electrostatics that is a problem that we are trying to solve. But this does work for many other cases. So this is the equation, and remember that rho is a function of all space variables, and phi we also seek to be a function of all space variables. Now this is one equation. So let us look at a different equation which has the form of Poisson equation, at least the same operator, a different equation. What is the different equation? Same operator, grad square. And in the right hand side, instead of minus rho by epsilon naught, what I have is minus 4 pi epsilon naught. I'm sorry, not epsilon naught, but the Dirac delta. In physics, we call it a distribution. We call it a function, but it's actually should be called a distribution. Okay, and I'm writing this x prime here, x minus x prime. X prime is just a constant when I write it this way. This grad square is operating on obviously x, and the solution for this equation I call g, and that will depend on x, and because I have x prime over here, it will change the solution. The value of the solution will change if I change x prime, so I just write it as g x x prime. Okay, so what are the commonalities, common things about these two differential equations? They have the same exact form. So let me call this equation A and this equation B. So what is common? The first thing is they have the exact same form. Operator on what you want to solve equals to a function, which you call the source term. What is the second thing? The second thing is they have the same operator also. Just to remind you one thing here, I never stress the following. So let me put the reminder here. We never said A and B has same boundary conditions. At this point, we are looking at two completely different problems, two differential equations, but there are some things which are common between them. They have the same exact form and they have the same exact operators. The source terms are different, and they doesn't have the same boundary condition. They not need to have the same boundary condition. We have not said that they have the same boundary condition. Okay. Now, you see, obviously, that why we are looking at equation B, there is a reason for that, and that is what Green did. It's not that we are doing it for the first time, and we'll see why we are looking at this. Now, this function, before we go ahead, this function which depends on both x and x prime, it's written with a capital G. It's called the Green's function. If you look at this equation, it looks exactly as the Poisson's equation. And if I replace, this is a Poisson equation, uh, with a point source, and the point source what is the strength of the point source? The strength of the point source is 4 pi epsilon. So if I put rho as 4 pi epsilon times delta, then we will get the right hand side here. And the source is at x prime, because that's in physics how we write a point source density. Rho for a point source at any point x for the source being at x prime is rho 0 times delta x minus x prime, and in this case just rho 0 is equals to 4 pi epsilon naught. So what capital G is the solution of Poisson's equation for a point source as x prime which has a certain source strength. So because of that, this also has another name called point spread function. And why it is called spread comes from really optics, but let's not go into that right now. It has also another name which comes from mostly its dependence, its time dependence when we will try to do the same solution for the dynamics case. From there the name comes kernel. We will discuss it when we try to look at the Green's function for the electrodynamics case. Right now we are looking at statics. Alright, so we have the Maxwell's equations, and then from there we have written down the potential formalism for the Maxwell's equations. Maxwell's equations in terms of the scalar and vector potentials. We realize that in a certain form, these have a particular structure which we can attack with this formalism called the Green's function to solve for these potentials. We have not solved it yet. That's what we will do in the next lecture.